Okay, in lecture video number 4, I would like to do an example problem that sort of takes us to the edge of how far we are going to take the vector mathematics that we're talking about. The r hat unit vector in particular we'll talk a little bit about in this video, but also in the following couple videos. So hopefully that will help clarify what exactly it means and what good it does us. I'd like to start out by having us recall that in Physics 140 there are two different ways that we encounter vectors, and so two different ways that we work with and do math with vectors. And the same will be true here in this course. The first way is that we take multiple individual vectors and add them together to get a single resultant. This is what would happen when you had multiple forces acting on an object simultaneously and you add them together to get a net force. Or, for example, if you had multiple individual displacements and then you ask what is the net displacement at the end of the trip. The second way that we would do mathematics with vectors is the exact opposite. We start with a single vector and break it apart into components. And again, the same will be true in this course. So let's take a look. For example, in video number 10 from Physics 140, which I linked as a supplemental video in the module on Friday, January 22nd, we had a problem where a pedestrian walks 9 blocks east and then 5 blocks north. And we're asked for the net displacement of this pedestrian. And the displacement is the straight line from the tail of one vector to the tip of the second vector. So the way we would solve this is we would say, first I would convert the 9 blocks. Each block, we are told, is 100 meters on a side. So I would convert this into a distance of 900 meters to the east and then 500 meters to the north. And the net displacement is that lighter purple or possibly pink colored vector that I've got on the screen right now. That is the hypotenuse of a right triangle. So to find its magnitude, I would use the Pythagorean theorem, meaning that the magnitude of displacement squared equals x squared plus y squared, where x is my 900 meters in the east direction and y is my 500 meters in the north direction. So the magnitude of displacement is equal to the square root of 900 meters quantity squared plus 500 meters quantity squared. And that's how I get that the magnitude of displacement is equal to 1029.56 meters. But in what direction? It is a vector, so I need to know the exact direction. So I decided to find this angle right here at the starting point, which means I can use sine or cosine or tangent to relate the three sides of this triangle. I happen to like tangent theta, which is equal to opposite over adjacent. So tangent theta equals 500 meters over 900 meters, or 5 blocks over 9 blocks. I'll get the same answer either way. So inverse tangent of 500 meters over 900 meters equals 29 degrees per my calculator. Or if you got 0.507, that means your calculator is in radians, not degrees. So you're doing it right, but you want to be in degrees, not radians. That's how I got these answers. Pythagorean theorem to get the pink straight line displacement, and the inverse tangent to get that angle down by the starting point. And again, we will do this exact same thing in Physics 150 with certain force vectors. I just want to make sure that we're reminded of how we were doing this. That's how we add two vectors. And again, the exact opposite is sometimes called for, where you're given a vector like this 10.3 units was given in this problem from the supplementary video that was posted on January 22nd. And we went back and found how to find the x and y components of it. This technique, again, is one we'll use in this course. So if you feel that that you are maybe not really strong on that material, you will want to go back and review it a little bit, but hopefully it'll be familiar enough as we go through our new sample problems that you'll understand exactly what we're doing. For example, using Physics 150 material for a question that would involve vector addition, I have a question like this one. Determine the net force on metal sphere A, that's shown here, that has 297 microcoulombs of positive charge if it has a sphere of 115 microcoulombs on its left and a sphere of positive 66 microcoulombs on its right, each 2 meters away from sphere A, and we put a sphere at the top of this page 3 meters away from sphere A and that last sphere has a charge of negative 81.2 microcoulombs. I'm going to take the words off the screen here so that we can have some room to work, but I'll label all of the givens that we had just read so we can see this. We have the negative 81.2 microcoulombs at the top of the screen, sphere A in the middle at the bottom with a 297 microcoulombs positive charge, and then the ones on either side of it, positive 115 microcoulombs and positive 66 microcoulombs. And the distances that we were given in the problem, 2 meters to either side of sphere A and 3 meters up to the top sphere. And so in this question, it's asking you to find the net force on sphere A. And this is really the exact same thing that you've done with complicated problems from Physics 140, where you may have had something like a rope with tension in it pulling a block up an incline with friction. There's a lot to do in a problem like that, but if we determine an x direction and we determine a y direction and we keep all of our calculations in the x separate from all of our calculations in the y, and we take it step by step, and we're careful with our calculations, no individual step of that would be difficult, and the same will be true here. So the first thing I want to do is establish that I'm going to call the horizontal direction my x, and I'm going to call my vertical direction the y. The first force I want to establish is happening to sphere A is that it's going to get pushed, it's getting repelled because it is positive and the charge on its left is positive. So it will feel a force from the charge on the left acting on sphere A. It will also feel a push to the left due to the charge on its right repelling it. So that red vector that I've drawn is due to the 115 microcoulombs pushing it to the right. And then the blue vector I've drawn, which I've drawn a slightly smaller amount because it's less charge pushing it, that's the force from the charge on its right pushing it away, so pushing it to the left. Then the third force that will act on this sphere is it will interact with the sphere at the top. Sphere A is going to be attracted to the sphere at the top of the page because they are opposite signs. So I've drawn these three vectors. I now know which direction each of these forces is going, to the left, to the right, and up. At this point, the negative or positive of each of the Q values stops having a useful meaning to me because I've already used that information for what I need to do with it. I have already established that the red vector is pointed to the right on the screen, and I've already established that the blue vector is pointed to the left on the screen, and I've already established that the green vector is pointed up. I did that by using the positives and negatives. So if I now take those positives and negatives and put them directly into the calculations again, I'm using them more than once. I'm using that same information more than once. And I don't want to do that. And we'll end up doing things like negating a negative. So when I say that I don't want to put the negative in the calculation, what I mean is I've already done that. I've already taken care of it. Now that I've got the green, blue, and red vectors, they can be treated without dealing with concepts like R hat. These can be treated just like a Physics 140 problem. A force to the right, a force to the left, and a force up. What do they add up to? In the x direction, my net force in the x direction will be the force that is blue on my page, which is the Q of the charge on the right acting on charge A, pointed in a negative direction from the perspective of Physics 140. I actually want to be able to add these vectors together in Cartesian coordinates. So at this point, I do want to think in terms of positive and negative x direction, positive and negative y direction. So I've got a negative direction force of the charge on the right on charge A, plus I've got in the positive direction force of charge left on charge A. And if I'm very careful about all of my numbers, I can put these in very carefully and get the correct answer for what's happening in the x direction. So in the negative direction, to the left, I have K times Q on the right times QA divided by the distance between them squared. That's what R subscript RA is the distance between the charge on the right and the charge A. And I'm adding to it a force that is pointed in the rightward direction, K times Q left times QA divided by RLA squared. If we put numbers in, we know the value for K is a constant. That's 8.99 times 10 to the 9th newtons times meters squared per coulomb squared. I know Q right is 66 microcoulombs. I know QA is 297 microcoulombs. and I know the distance from the charge on the right to charge A is 2 meters. So I very carefully put all of that in and say that is happening in the negative x hat direction, and then I'm adding to it what's happening in the positive x hat direction, which is the k times q left, which was 115 microcoulombs, times qa, which is 297 microcoulombs, divided by the distance between them squared. That distance was 2 meters. When I add these all together, I multiply out all the values and add the two forces together, I get that in the x direction there is a net force of 32.7 newtons, and I get that it is a positive x hat direction, meaning that these two add together for a total force in the right direction on my screen. And that should make sense because I said that the red vector that I drew on there should be bigger than the blue vector that I drew on there. I know that because sphere A is getting pushed more by the 115 microcoulombs than it is by 66 microcoulombs, by virtue of the fact that they're the same distance away, but one of them has more charge. The one with more charge will push harder. That is the one on the left pushing, therefore, to the right. That's everything that's happening in the x direction. In the y direction, the net force on sphere A is that it's getting pulled upwards by q top. So q top on qa is going to be found with Coulomb's law, k times q top times qa divided by the distance between them squared. So q top was given as 81.2 microcoulombs. And again, I don't want to call that positive or negative here. I'm just looking for the magnitude because I already know the direction. The 297 microcoulombs, of course, is charge A, and then the 3 meters between them then gets squared. And it says x hat. I'll fix that before I put it in the notes. That should say y hat here on the screen, right, exactly where it is right now. That comes out to 24.0 newtons y hat, meaning that sphere A is experiencing a net force of 32.7 newtons in the x hat direction plus 24.0 newtons in the y hat direction. And if you remember how we deal with vectors, that is a legitimate way to report a net force, is to say this much x hat, this much y hat. If we were really asked to add those together to give a single resultant, like we had done with the pedestrian displacement, we could go back and find the net force using the Pythagorean theorem, saying 32.7 newtons squared plus 24 newtons squared would give us some net force squared. And we could find the exact angle. We weren't asked that here, so I didn't do that. That is the extent of what we would do with adding forces together. That is like the hardest that we could possibly make vector forces in Physics 150. And it should look a lot like the hardest problems we did with adding forces together in Physics 140. So what I'm saying is you should be capable of doing a problem like this, but I'm also going to say this is much longer than what I would ask you to do on a test. It's just a very lengthy process. So this isn't really the focus of what we want to do in Physics 150, and we won't spend a lot of time on it. But if you can't do this type of problem, then it does show a gap in your physics knowledge. You should look at this as a problem that is complicated and lengthy with a lot of individual steps, but hopefully each individual step makes sense to you. That's where we really want you to be.